Imagine that you're a hiker who has lost their way, and all of a sudden you come to this vantage point where you can see clearly the surrounding area, and it becomes clear the direction you need to take and what the layout of the land is that you're approaching. So similar to this, summary statistics give valuable insights as one of the very first steps in data engineering after we gather the data. So if we look at the map of machine learning and data science, we have our data, and then after we combine data sets and consolidate, then we want to look at statistics to help us with the data assessment. How good is our data? How much data diversity is there? Are there outliers and other things, just to be able to see and understand the data. So we're going to use packages such as numpy, pandas, and Pandas Profiling to help with some of the statistical analysis, so we don't have to start from scratch. There's a couple links here just to use some of these packages to show numpy, pandas, and Pandas Profiling. If you need to install those, then you can do pip install numpy, pandas, and Pandas Profiling. Chances are the only one that you may not have is Pandas Profiling. So let's just go here to the Google Colab link, and I'm just going to start here with the first cell. It says it's not authored by Google, and you can go ahead and click Run anyway. Okay, so all the requirements are satisfied. I'm going to come here and just do read in the data, and then we'll describe it. We'll use a data.describe. Now that it's a pandas data frame, we can do some summary statistics. And this is very nice because it gives us the data count, the mean value, standard deviation. We have the min, max, and then the quartiles in between for our data. So this is the week number. It includes the year, so it isn't very meaningful right here. The more meaningful one are going to be the cases. Okay, so the mean number of cases by state, and then we also have the incidence per capita. So that's the number of cases divided by the population. And we can also use Pandas Profiling. We're going to use from Pandas Profiling import profile report, and then we're going to create a new profile. And one of the things they've put here is just a try and accept, because some environments like Colab won't allow the widget. And so we have to export it as an HTML file, and then we can open it. But let's just do that. We'll have a warning here that says that it isn't available. Okay, so it's not yet fully supported on Google Colab, but it's going to generate this and send it to this file, data.html. And then after it renders this, then we'll be able to see the report. Now, for some very large data sets, we want to put on here explorative. Okay, that's going to be true. And then minimal, you could also set that to true. If it's very large, it'll get rid of some of the analyses like the correlations, and others that take a long time to calculate. Once that's done, though, you can come here to Files, and there you'll see your data.htm, and then we'll just select Download. And it'll download this, and then we can open up the summary report. Okay, I'll just go ahead and open this, and you can see an overview. There are some alerts. Okay, high correlation, constants. 64% of these have zeros, which isn't a problem. Sometimes those months will report 0 cases. And also the incidence per capita also has a number of zeros as well. All right, and then we look at the individual variables. Okay, this is the week. We don't have to pay attention to that. It's just a code for the year and the month. Okay, or the week in there. Okay, then the state as well. Okay, here are the different states, and they're fairly evenly distributed. Kansas apparently has the most. And then we look at the state name. Okay, we have disease. It's just going to be smallpox. It's excluded because they're just constant values. We're only looking at smallpox for this one. So it said you can safely ignore this one. These are the cases. So you can see the distribution in cases. Most of them are 0. And then it tails off to, looks like around 2 to 300. Okay. And there you can see the maximum is 350. You can also see the incidence per capita. And then we can do some interaction plots. Although these aren't very meaningful here because the data is mostly skewed toward the 0 side. And we'll explore some things with this data later to address that. Okay, so if you want to run this as well, okay, I'm going to just come and leave this, come to the notebook, and then if you come here, you can right-click on raw, and then save link as, and then you can save it as summary statistics.IPYMB. I've already downloaded this and opened it, so I just wanted to show it to you here in this local way to run it, and I'll just do kernel run all and run all the cells. Okay, so it's going to try to install these as they're already satisfied. If it does install something, you'll have to just come to kernel and then restart the kernel and then run it again. Okay, you only need to install it once. Here's my data table, my data frame, and then I'm going to describe it. And then here you can see it's going to do it as a widget. So it's going to be here right in the Jupyter notebook, which is nice because then you don't have to open up a separate HTML file. Okay, and we can see things like correlations. We can look at the different types of correlations here. And then we have some missing values and samples. This just produces the top 10 data rows and then the bottom 10 data rows. Okay, so that's just the basic statistical analysis and summary. We're going to get into a little bit more detailed case study here as well. But let's go through some of the material. Okay, it shows Pandas Profiling. We have this activity here. This activity uses summary statistics to analyze disease spread in the U.S. states with smallpox data. As we mentioned, this introductory exercise analyzes data specific to the state of Utah, and then you'll be able to change the state to another one, perhaps one in which you live or that you like to visit, and just see how those trends compare. Okay, so if we come here and open up this link, go to raw and save link as, and then you'll get this review math and stats. Go ahead and click save. I already have it downloaded and opened. Okay, so we're going to just start with importing this data table again. Go ahead and run it even though the results are already there, and then describe the data. Make sure you get that same result. Okay, and then this Pandas Profiling, just like we mentioned before, here's the same profile report. And then we're going to get down here to the mathematics. And let's do a quick review on the mathematics and talk about the different types of variables that we're going to be typically encountering in data science and machine learning. So we have things called scalars. Those are just a single value. And then vectors, those are one-dimensional matrices or arrays of numbers. So just a series of numbers like a list. And then matrices are two-dimensional or multi-dimensional, and those are often these rectangular arrays of numbers arranged in rows and columns. And they're typically denoted with bold capital letters such as A or W. And in Python, matrices and vectors in the numpy package are called arrays. And then when we're dealing with a table in Pandas, it's called a data frame. So we're going to first of all just look at Utah cases. Okay, and we want to filter by state equals UT. So I'm just going to come up here and show, okay, so I've described this. Here's my state abbreviation. So we could also do it by state name and put Utah in there. But I just want to filter out just the ones that are equal to Utah. And we can pick a different state as well. All right, so what we want to do now is create a matrix of the data from cases and incidents. I guess that's spelled wrong. Incidents per capita columns. Okay, so let me just correct that. Okay, it's in the comments anyway. But we're just taking just those two columns and we're getting the values of those. And we're going to print the matrix. You can see these are just all the rows. And we can also print the shape as well, matrix shape. So we have 1055 by 2. And the first column is going to be the number of cases. And the second column is going to be the incidence per capita. All right, so the vector is composed of the values in the 0 column. That's the first column of the matrix. We'll use this colon to say, I want all the rows, but the first column. And that's going to produce a vector. And so let's do the same thing to just get the number of cases. So I'm just going to get this very first column right here by saying I want all the rows and just the very first column. And I could change that to the second column as well by putting a 1 there. And then that would get all of these values. Now you see I have just the first dimension, which is the number of values, and then there's a comma with no value there. So that is implied that there's just one value there, or it's just a vector. Okay, it's an array with just a single dimension. Okay, so I'll switch this back. There's my vector, and then we want to create a scalar out of the sixth attribute of the vector. So Python starts with the number 0, so we'd use bracket 5 to access the sixth value in the array. Okay, and so that's a scalar, and the shape, you can see it's an empty tuple there. It just means it's a single value. All right, and we can also print the type of scalar, and there you're going to see it's just a float, a numpy float, 64-bit value. All right, so let's go on to our activity now. This one is going to be to create an X matrix out of the cases and incidents per capita columns of a state of your choice. So we can choose one. I'm going to choose Texas for this one. And this is going to be data. And I'm going to filter it by the data where the state is equal to Texas. Okay, and if I just said Texas head, I can see that I've just filtered it out. So row 37, 80, 123, 170, 217, those were all Texas. And these are going to be the smallpox cases for that. So now that I've created TX, now what I want to do is just create X, and that's going to be TX. And I want to just take cases and incidents per capita. All right, and then I can do x.head. So I just want to just take those two columns only. All right, and if I also just say dot values, then it converts it to a numpy array. I've just extracted the values, and so it just stores it a little bit differently. Instead of as a data frame, it's just going to convert it to a numpy array. All right, let's also, I'll insert a cell below, create a vector containing all the values of instance per capita column of X. So I can do this one of two ways. After I convert it to a numpy array, then I can just say I want all the rows and then the first column. Okay, that's just going to take that, second column. That's a 1 in Python. Or I could just say, let's see, if I just wanted to do this as a data frame, I could do incidents per capita. Okay, and that would give me this essentially a data frame with all those values. Okay, and then I could also say dot values. So that's one way to filter out which column you want. You can do it any of these ways to get that vector of values. All right, I'm going to insert a new cell here, and let's just create a scalar. We want the x12 from the 12th value, and remember to use x bracket 11 to get that. So I'm just going to say, after I've named this x and run it again, then I want to get x11. Okay, so there's the 11th value of that array. Or sorry, the 12th value, I put 11 in there to access the 12th value. All right, and then let's just do one more. We want to find the dot product between two distinct vectors in matrix X. It may be helpful to import numpy and use np dot dot. Okay, so the dot product between those, and I want to just include, let's see, I could name it X and then Y, for example. Just to get those two as separate vectors, and then I can multiply those two together to get the dot product of them. So it's going to multiply the instance per capita times the cases and then add them all up. Okay, so that's what the dot product is going to be for this case. Okay, let's go on to the next section, which is summations and products. This is a little bit of a math review, but I just wanted to share this notation. If you have a vector and you want to sum that, you use this capital sigma to do the summation from I equals 1 to n. And it just means that we're adding up all of the values in our vector. And similarly, the product, okay, capital pi, is just the product of all those values. So this is common, especially the summation. If we want to take a data column, we just want to add them all up. And we can do that a couple different ways. Here's the Utah summation. The other way we can do this is cases.sum. Okay, so you could either do it with a data frame, and then it has a method, the summation method, or you can do the numpy around it and numpy sum around it, and then get the summation. All right, so let's find the total number of cases in another state. So let's just copy this and change it to Texas. And that's going to be the Texas cases, and we'll do the Texas sum. Okay, so Utah had 896 cases. Texas had 14,169 cases of smallpox, larger population overall, so that's not surprising. Okay, let's go on to derivatives and gradients. One of the things that we commonly compute in machine learning are going to be derivatives, especially for training neural networks or others. We'll use automatic differentiation to obtain those. But sometimes we even want derivatives to be able to derive features that can explain something. So how rapidly something is changing. For example, let's say there's an outbreak in an area, and you're trying to use that to predict something that will be able to show what is the rate of change of the disease spread. So we're going to look at derivatives and gradients here. The first thing that we're going to look at is sorting. For example, sort values by week. What we can do is we can sort the data according to the week with this by week. So it takes that column of the data frame and is going to sort it. And then we need to do that because then we're going to take the difference. Okay, so from week to week, each consecutive week, we're going to look at the difference between those two. So it's like a finite difference of how much change there was in the number of cases. And we're going to call that d cases, okay, the derivative of the cases. But we can also have multiple weeks. So sometimes they skip reporting a week. So what we might need to do is look at the difference of those and then divide it by the number of weeks. Okay, so then we can plot this numerical derivative, this finite difference approximation, which is the derivative of cases divided by a derivative of weeks. And we'll just do a plot of that. So this is our result for Utah. And what we want to do is find the weekly difference in smallpox cases for the state of your choice. Calculate the numerical derivative, finite difference, for weekly smallpox cases. And we'll plot the numerical derivative for weekly smallpox cases. We'll interpret, say some things about the graph. Okay, so what I'm going to do is basically just copy this, okay, and change it to Texas, all right? And I can, here I've got that right here just to speed this up a little bit. Okay, the same things, but just with Texas in there. And you can see the changes right here. All right, but now what we want to do is you see a lot of noise in there. Maybe week to week, just 1 week isn't good enough. Maybe we want to look over a period of 10 weeks instead. So let's just copy this and change a single parameter on our diff function to include periods equals 10. So I want to just have periods equals 10 for each of these. And here we're going to see it smooths it out a little bit because we're looking over a longer time periods and say, what's the change over 10 weeks? Okay, so it reduces some of that noise that you see just from week to week. All right, let's look at some things about statistics and distributions. So a distribution describes the makeup of the data in each column. Distributions can either be discrete, set numbers, or continuous. All numbers in a range are possible. So we'll plot these distributions, see what the data looks like, but then we'll also do some summary statistics as well that can help us decide, what's significant about the data, are there outliers and other things. So this is a little bit complicated, but I have all of the data where it's not equal to 0. Okay, so maybe I'll separate this. Non-zero equals, I'm just going to put it here, Utah is incidence per capita, not equal to 0. And then I'll put in the non-zero values here. Basically, these are just ones or zeros that tell me if it's 0 or not, and whether it should be included. So that gives the same results as before. Now what we want to do is plot the distribution of incidence per capita for the state of your choice. And sometimes the log scaled values are more useful and give better results. So we want to take a look at the log scale of the incidence per capita and observe the difference. All right. So let's just do this for Texas as well. I'm going to take all of my values where they're not equal to 0, changes to Texas, and have this histogram plot. Okay, so the .hist, that creates a histogram of my data. So you can see that most of them are very low, but let's do the log scale of this as well. Okay, so I'm going to just insert a new cell below, and let's just look at Texas, and I'm going to call this log incidence per capita. And there's a way to do that. We can do np.log, okay, or you can do log 10, for example. This is going to be the natural log. Texas, and I'll put in my non-zero values, and this is going to be incidence per capita. Okay, and then if I just come here, I could just say, let's just look at those. I'll look at my head. Okay, and it calculated the log of that incidence per capita. Took this number, just did the natural log of that. All right, and then let's do the distribution of that. I'll just do, I guess I want just the non-zero values. And I'll do the histogram of that. Okay, did all of these, but here you can see the incidence per capita. If I just want that one, I can put another bracket in here and just get the log of the incidence per capita for the non-zero values. So here it is in the log scale. So that looks a little different than this. It's just taking the log scale, and sometimes this transformation helps you get a more normal distribution or other things that are helpful, because we don't want to necessarily favor zero or very low cases. We want to try to predict higher cases, for example. All right, let's look at some of the things like mean and standard deviation. We're also going to look at other features like kurtosis and skew to be able to describe deviations from normal distributions. They're not only useful for describing data, but you can potentially use them as features to help you predict something. So for example, in machine learning, it can help you classify or do regression. So here's a description of the Utah cases. And then I'm just going to do the non-zero cases, and there you can see just the non-zero, and it has a different count. Okay, so the non-zero are only 216 weeks, but all cases are all counts is 1055. So many of those are zero. What we want to do is display the mean, standard deviation, quartiles, max and min for the data in another state besides Utah. And again, we're just going to continue with Texas in this case. We'll save the statistics as variables for later use. So we're going to use Utah cases, for example, the mean, standard deviation, quantile, max, and min. And we also want to find the kurtosis and skew of the data. So we're going to use .kurtosis and .skew. So we can say tx mean, for example, is going to be equal to tx cases and dot mean. All right, and if I print that out, tx mean, then I see that's 13.31. But if I wanted to say just the non-zero values, okay, for Texas, I think let's see if I still have that as non-zero, then you're going to see that's going to go up. So if I just excluded all the non-zero, then I get the mean values for those. But let's just include all the zero values in here as well. Okay, so the next one, I'm just going to leave out the name like this just so it'll print out. I'll do Texas cases, and then let's just do standard deviation. All right, and if we do Shift Enter, it gets us a new cell, and then we can do quantile. This one will give us the median value, but if we want the third quartile, the start of that, or we can put in 0.9, the 90th percent quartile, that's going to be 39, or the 10th percent quartile, or anywhere in between. So that gives us the quantile of any fraction between. Sometimes the quartile, we just do like 0 to 25%, 25 to 50, 50 to 75, and 75 to 100. But this gives us an opportunity to put in a continuous value anywhere between 0 and 1 and get an idea of the quantiles. All right, and then that's going to be equivalent, if we just leave this out, it's going to be the 50th, basically the median value, and we could also do median as well. Okay, so here's the same value that we got. And then we can also do the max and the min. And then also the min value. All right, and then let's also do the kurtosis. Kurtosis is one you may not have heard of before, but what it's doing is trying to help you describe, does it have a normal distribution? Is it Is it more heavy on the tails or more heavy away from normal, more in the middle? Okay, so if you have a high kurtosis, then it basically means you have something very skinny and tall with very little tail. And if it's anyway, 3 is kind of the normal distribution, and if it's less than 3, then you have more in the tail area. So if we looked at Texas cases, let me just do this again just so we can see the distribution, and I'll do the histogram. Okay, so it has a very narrow distribution right here, right around 0, and then very few tails. So this kurtosis is very high. And so it tells us that with just a metric, even without looking at the histogram, it'll tell us, well, we're at a 32. So it's very narrow, sharp peak right in the middle and very little tail. And if it's less than 3, then it says, well, there's a lot of tail here, very little in the middle. It's relative to the normal distribution. Okay, in Excel, if you calculate this in Excel, they subtract 3. So if it's 0, then it means it's normal. And if it's, so some packages are different than others, but in Python, at least in this one, for data frames and in Pandas, it uses 3 like most other statistical analysis software. Okay, I'm going to go down to the next one, and I'll just show you one other thing that you can do as well. You can do skew as well, and so this one is going to be another metric that helps us determine if it's skewed to the left or to the right of normal. And so the skew value, typically it's 0 to 0.5 or negative 0.5 to 0.5. It's very little skew. If it's negative 1 to 1, it's kind of a moderate skew. And if it's outside that absolute value of 1, then it's heavily skewed toward one side. And so you can see in this case, it's heavily skewed because we don't have a tail on the left side. So the skew is very high. But sometimes what we want to do is not look at the raw values, but maybe a transform of those. So let's just take the log transform like we did before. This is just going to be Texas. We'll look at Texas cases, and where they're not equal to 0. And we will look at cases dot values. Okay, we'll take the log of that. This is going to be a vector of values, of all those log values, okay, that we saw before. And let's do Shift Enter to create a new one. Let's just look at the distribution of those. And I'm going to do this with matplotlib, pyplot as PLT. And then if you want to do a histogram of C, it's going to come up with this distribution here for Texas. All right, let me come down, create a new cell, and then we can use SciPy stats to calculate the kurtosis. And SciPy.stats will import kurtosis and then calculate kurtosis C. Okay, so there's our kurtosis now of this transformed. So this says that we're more heavy on the tails now. It's below 3, so it's heavier on the tail versus a normal distribution. So it's very flat here. All right, and let's do the skew as well. We're going to do the same thing with SciPy stats. We'll import skew, and we'll calculate skew of C. And there you can see the skewness of this. So it's a lot less skewed. It's more normal in terms of equal on the right and left. There is more here toward the lower values. Okay, so that concludes the math and statistics review for machine learning. It's this part right over here that we see on the right as we're going through data engineering. this is our critical one right here, the data assessment. How good is our data? And then if data is not very good, then we may need to increase the data diversity, collect more data, or do feature engineering as well. That's going to be able to help us develop new features such as the log transform, or maybe the multiplication of two variables, to be able to get better explanatory variables for our predictions. All right, and we'll also cover next visualization. We did a little bit here, correlations, distributions, pair plots. That'll also give us some insights about the data. And then after that, we're going to come down here to cleaning the data, okay, and removing outliers and putting on different filters for the data. We'll scale the data. And then once we have scaled data, then we can split the data into train, validate, and test sets. And then from there, we can go on to creating our labels and our outputs, the things that we're trying to predict. Also, we have our features, and then we can do unsupervised, semi-supervised, supervised learning with classification, regression, or clustering. There's also dimensionality reduction that we can do as well. So this is the overall flow chart, but I just wanted to show you this because statistics, right here, we have our statistical analysis. That's a critical first step before we even get to these other things. We want to be able to understand the data, much like that hiker who came to the summit and saw where they're going, where are their potential pitfalls, and we want to do the same thing with our data as well.